Assalamu alaikum. Welcome to lecture number 26 of Digital Signal Processing. In this lecture, I am going to discuss the relationship between impulse response and frequency response. Although we have two types of impulse response, that is finite or infinite. So whether we have finite impulse response or infinite impulse response, how we can determine the frequency response with the help of impulse response, we will going to learn in this topic. After that, we will discuss the second most important representation in time domain, which is the difference equation. In this topic, I will discuss the standard or generic representation of difference equation. Then I will discuss the representation of difference equation for FIR filters, and then the difference equation representation for IIR filters, and what's the difference between the two representations. Then I will discuss how we can determine the order of any discrete time filter or system. By the term order, I mean to say that how much poles or zeros are there in the system, and poles or zeros basically determine the characteristics of any system. So that poles and zeros will be decided by the order of system, or in generic term we can say the sharper response means the order of the system is higher. So if we need a sharper response from any system, then we must design a system which have higher order equation. After that, I will discuss the relationship of convolution to FIR digital filters. You must remember the convolution topic we have discussed in earlier classes. Now I will connect the convolution with the difference equation of the FIR filters and how these two equations are similar and which parameters we can deduce due to this similarity. So we will discuss this in this topic. After that, I will discuss the difference equation and FIR filter coefficients. From this I will derive the method, or I will tell you the method. So how you can derive the FIR filter coefficients with the help of any difference equation. Previously we learned to determine the impulse response with the help of difference equation, and now we will learn in this topic that how we can extract the system coefficients or filter coefficients with the help of difference equation. So proceeding to the lecture. In the last lecture, we have concluded our discussion with the first method of determining the characteristics of any black box or any system for which the expression is not given or its characteristic is not defined earlier. So to treat that type of system, we have first method already discussed in the previous lecture, which was applying different types of input and note the corresponding output, and with the help of the accumulated information we can actually plot the frequency response and can tell about the characteristics of the system. That method was although real-time scenario, but it is not practically possible and it is not very efficient also. So we need some efficient method to determine the characteristics of nature of the system if that is not provided to us. Recall we have considered system as a black box and we are interested in determining the nature or characteristics of that black box or that discrete time system. So the second method, which is more convenient and more efficient, is by applying impulse at the input to that system. Recall the concept we have studied earlier, that the impulse in time domain is actually the constant line in the frequency domain. We also discussed this concept in very detail, that when we apply impulse to any system, then it actually means we are applying all the possible range of frequencies to that system. So from that we actually learn the behavior of the system on all the possible frequencies. So we are using the same concept here, and by using the same concept we are applying impulse at the input of that black box or that discrete time system for which the characteristics is unknown to us. So when we apply impulse as an input to the system, then actually we are applying all the possible range of frequencies. This can be achieved when we take the FFT of this impulse response. For this impulse, we have certain kind of impulse response. So this is the impulse response. This is assumed to be the impulse response, as this is not the specific case. We have generally considered a random impulse response or random sequence as a impulse response. So for our assumption, we are assuming that for this kind of input to a particular system, a system is producing this kind of output, and this kind of output is due to the application of impulse at the input side. So this comes to be the impulse signal, which is delta of n, and this becomes h of n, which is impulse response. I hope that this concept is clear. This is the impulse signal which is applied to the system, and due to this impulse we are getting this response, which is impulse response, because we are applying impulse at the input. Now if we take the FFT of this impulse function, actually then we already know that we obtain a constant line or DC line which covers entire range of frequencies. And interestingly, if we take the FFT of the impulse response, then actually we will get the same frequency response we were getting previously in the first method, which was not a practical case. We can see the other side of picture also by this frequency domain view of both the impulse and the impulse response. For example, this impulse signal is providing us a constant or DC line in the frequency domain. So it means we are applying all the possible range of frequencies to that system. This is very much similar to the first method, in which we are varying the frequency from 1 Hz to 10 Hz to 100 Hz to 1000 Hz and so on, and we were doing it manually. And here this process is now automated. How? The all possible range of frequencies is applied to the system just by applying a single impulse at its input, because this impulse function appears to be all possible range of frequencies in the frequency domain. So this means in the frequency domain we are applying all possible range of frequency, which is very similar to the procedure we were doing in the first method manually. So we are getting the same response which is achieved in the first method, but that was not practical, and this method is very much practical and efficient. We just have to apply single input, and that input is a unit impulse signal, and for that impulse we obtained some impulse response. What we need to do? We just need to take the fast Fourier transform or FFT of that particular impulse response, and by taking the FFT of that particular impulse response and the FFT of the impulse response actually gives the frequency response of the entire system. So we can say the impulse response in the time domain, which is represented by h of n, and by taking its fast Fourier transform, which is FFT, we will obtain h of f, which is the frequency response. So this is the very shortest and the efficient method to determine the frequency response of any system, and this is how the impulse response is related with the frequency response. Impulse response is in the time domain, and if we take the fast Fourier transform of that impulse response, we will obtain the frequency response. So one is the time domain view and the other is frequency domain view. So that is very much interesting. So this is the shortest method as well as the fastest way to determine the system characteristics is to take the FFT of the impulse response. And how we get the impulse response? Just by applying an impulse at the input and observing the corresponding output, because that output is the impulse response. Up till this slide, we have learned the time domain representation of any discrete time system in form of impulse response. In this slide, we are going to learn to represent the discrete time system with the help of a difference equation. However, we already looked at a different relationship between the impulse response and difference equation. But here we will see the difference equation of any discrete time system in more detail. Difference equation is actually the mathematical relationship between discrete time input and output signal, obviously with some coefficients. As you can see that this is the generic difference equation which can represent any discrete time system. Here x of n is treated as input and y of n is treated as output, and x of n minus 1 and its variant is treated as the delayed version of input, and y of n minus 1 and its other versions are treated as the delayed version of output. As you can see, the coefficients attached with y of n is with negative sign, and this negative sign is actually because we are actually shifting these coefficients from left hand side to right hand side, because all the coefficients of y of n are on the left hand side and all the coefficients of x are on the right hand side. So after shifting the coefficients of y, which is the delayed version of the output or advanced version of the output, to the right hand side, these coefficients become negative, because we are more interested in the actual output, not the delayed version of output or not the advanced version of output. So to determine the actual output, we represent this difference equation in the standard form. And if you can see that we have several coefficients associated with several time delays of the input signals, and several coefficients along with its delay is associated with the output signal. So all these coefficients and its delays can be represented in a generic form with the help of this summation sign, and b of I is actually representing the coefficient associated with the input, and I is basically representing the delay, number of delay, how much delay this input is getting, and this can be vary from 0, which is no delay in the input, to m delay in the input, and m is the arbitrary value, and same is the case with the output samples. A of j is basically representing the coefficients associated with the delayed version of output, and y of n minus j is basically representing delayed version of output, and j can be varied from 1 to n. J cannot be 0 because 0 is incorporated on the right hand side, that is the actual output. So j will always start from 1 and it can vary from 1 to any arbitrary value which is treated as n. Another interesting part of this equation is its recursive part and non-recursive part. You can see the first part or the part associated with the actual input or delayed version of input is termed as non-recursive part, and the second part, which is associated with the delayed version of output, is termed as recursive part, and it is always with the negative coefficients. So difference equation can be divided into two parts. First one is recursive and second one is non-recursive. Or individually, we can denote each coefficient as y of n is treated as the current output, a of j is treated as output coefficient, b of I is treated as input coefficient, and a of j and b of I, which is the output coefficient and input coefficient respectively, can be collectively called as the system coefficient. So this a of j and this b of I is actually the system coefficients. Further, y of n minus j is the previous output and x of n minus I is the previous input, and this overall equation is the generic form of difference equation for any infinite impulse response filter or system. Why I am saying that this particular expression belongs to infinite impulse response system? Because in this equation you can clearly see we have the previous output or some feedback in terms of delayed version of y of n. So as this equation is depending upon the previous output samples, or in other words this equation is having some feedback, so this overall equation is the generic form of difference equation for IIR filters. But if we talk about finite impulse response filter, then you can easily say that for finite impulse response filter, this recursive part is equal to 0, because there is no feedback or no previous output sample fed back again to the at the input side to FIR system. So if we are considering the FIR system, so y of n is equal to only the recursive part, and if we are talking about the IIR filter or IIR system, then equation can be represented just as written in this slide. I hope that this concept is clear to you people, that for IIR system both part remains there, which is recursive part and non-recursive part, and for FIR system, which is finite impulse response system, this recursive part will be equal to 0 and we only get this non-recursive part. Moving on to the next thing, which is order of any discrete time system. We can actually determine the order of any discrete time system with the help of its difference equation, and it can be found with the amount of shifting. As you can see, order is equal to maximum of m or n. So actually what happens, the proportion by which we are shifting the input or output, the poles and zeros are generated in the same proportion. And what are the poles and zeros? These zeros and poles actually determine the frequency response. We will see the sum plots of poles and zero in the later lectures, but for now just understand, as the number of poles and zero increases, So actually delay increases, and it means we have a sharper response. So if we need any system to behave very sharply, or which can select the frequency very sharply, so we need to increase the number of zeros and poles, and this can be increased by increasing the number of delay, or we can say as we increase the value of m or n actually, which is the delay, so poles and zero of system increases. So if we want a very perfect system which gives us very sharp response to a particular frequency, we need to design system which have higher number of zeros and poles, obviously, which is a complicated design. For FIR filters, we already know that the recursive part tends to 0 or equals to 0. So the equation remains with only the non-recursive part, which is the delayed version of input, which is x of n minus I, or we can say x of n minus k if we assume the delay variable as k. So for FIR filter, recursive part is 0 and the equation becomes like this as displayed in the slide. And if we look at this equation very carefully, then this equation is very much similar to the convolution formula. I have also added the convolution sum formula below the difference equation. Here you can see the delay is represented by k, and the formula is summation x of n minus k into h of k, and all the delayed version are actually multiplied and then added, and the same strategy is applied or represented by the difference equation of FIR filters. So we can actually, by the same nature of these filters, we can compare the two equations. One is for FIR filters, for which recursive part is equal to 0 and we only remains with the non-recursive part, and this equation can be compared with the convolution sum, and after comparing we get to know that actually bi, or we can say bk if the delay variable is k, bk is equal to h of k. So actually the impulse response, which is x of k, is equal to bi, which is the system coefficients. As we already discussed that the coefficient associated with the delayed version of input are the input or output coefficients, or in general we can say these coefficients as the system coefficients. So we can determine the system coefficients with the help of impulse response. So this is very amazing that by means of difference equation we can actually calculate the impulse response of the system, and if impulse response is given to us, we can actually determine the system coefficients. How? We will see it in the later slide. In the previous slide, we have learned that the filter coefficients can be extracted with the help of impulse response in time domain, and the relationship is again presented in this slide, that is bi is equal to h of k. So we are talking about FIR filters, and for FIR filters it is true to extract its coefficient with the help of impulse response. Now graphically we are going to learn what's the relationship between the time domain and frequency domain factors or parameters, and how we can transform from one domain to another with the help of available parameters. So look at this graphical representation very carefully. Suppose we have some input sequence which is represented by x of n. Now this input sequence is fed to a block, which is, you can see, denoting the convolution process, and it is convolving with actually the coefficients of hk, which is the impulse response. We already know the coefficients of hk is basically the sequence representing the impulse response, because impulse response in continuous time is represented by h of t, and the coefficients hk is actually the discretized version of h of t. So the discrete sequence of impulse response or discrete version of impulse response is actually convolving with the input sequence. You can see here is the input and here is the coefficients hk, which is nothing but the discrete version of impulse response. So these two are fed up to the convolution block. Here steric sign is representing the convolution process. Please remember that steric is always used to represent the convolution process. Now after convolving the two inputs, which is the first input signal and second one is the coefficients of impulse response, we will get the filter output sequence in the time domain. This is important as we are convolving the two sequence which are in time domain, because impulse response is in time domain and the input is also in time domain represented by x of n. So the final version after convolving is also in the time domain, and you also know that convolution is used to produce the third signal, which can be the result of input signal and the impulse response of the system. So in this way we are getting the final output in time domain. Now what we are doing with this output, we are taking the Fourier transform or DFT of this output, and after taking the DFT of this output we can actually convert the output from time domain to frequency domain. Here you can see the final output is converted into the frequency domain. Usually we denote small caps for time domain and we use the capital letter for representation of frequency domain. So you can see that y of n is in the time domain, and after taking DFT or FFT or just by transforming it into the frequency domain, we will get the output sequence in the frequency domain. Now if we again take the inverse of this frequency domain output, we will again transform back into the time domain, because we know that when we take the DFT, we convert the samples from time domain to frequency domain, and if we take the inverse DFT or inverse FFT of this frequency domain version, then we will transform back to the time domain. Now the other side of picture is this. Suppose we are not convolving the two inputs, but we are first taking the transform pair of these two inputs, which is the input sequence and the impulse response. So if we take the FFT of input signal, you can see that here we are taking the DFT of our input signal, then our input signal is actually converted into the frequency domain representation, and same we are doing with the coefficients hk, which is the impulse response and time domain. We are taking DFT of the impulse response. So by taking DFT, we are actually converting the impulse response into the frequency domain. So here we get the frequency domain version of these two inputs, which is the actual input signal and the impulse response, but both are in frequency domain now. As you can see that there is a dotted line which is representing all the blocks above this line are in the time domain, and all the blocks and processes below this line are in the frequency domain. So here we get the frequency domain version of input signal and frequency domain version of impulse response. So we are interested in the final output. So what we have to do, we just have to multiply the two frequency domain version or two frequency domain outputs to get the final output in frequency domain. And if we want to again transform back into the time domain, for example, if we want the output in time domain, we just take the inverse FFT of this final output to transform back the final output into the time domain. So here you can actually notice that if we are convolving two signals in time domain, then actually multiplication happens in frequency domain, and we are ended up with the same results with both the operations, whether we are convolving two signals in time domain or whether we are multiplying their spectrum in frequency domain. Both are same. The difference is basically the transformation from time domain to frequency domain. When we just convolving the two signals in time domain, we get the output in time domain obviously. But when we are multiplying two signals in frequency domain, we are obtaining the same output, but that output is in the frequency domain obviously, because we are multiplying two spectrums. So two spectrum multiplication will yield another spectrum. So we will obtaining the output in frequency domain. So here is the conversion from time domain to frequency domain. If we take the inverse FFT of this frequency domain version, we will transform back to the time domain, which is same as the result of convolution of these two signals, which are input signal and impulse response. So if I want to conclude this graphical representation, I can say the convolution in time domain is equal to frequency domain multiplication, or the multiplication in frequency domain, or vice versa. It is very interesting to note that the vice versa of this operation is also true, which means if we multiply two signals in time domain, then convolution occurs in frequency domain. So these two are the transform pair, which is convolution and multiplication. If we are multiplying two signals in time domain, then actually their spectrum will get multiplied in frequency domain. Or if we are convolving two spectrums in frequency domain, then actually multiplication of two signals occurs in time domain. So this is very important building block of DSP also. So I want you people to grasp this concept very strongly, that the transform pair of convolution is multiplication. Convolution in one domain results in multiplication in other domain. So I want to end up my discussion with the note that if you want to ask anything related to this lecture, or if you want to clarify further regarding any slide, you may email me or you may ask me in the live session. Thank you. So here you are provided with two examples. In first example, impulse response is given as 1.9, and this is the same impulse response we already discussed in previous slides. So by using the same impulse response, we can actually compare the results also. So that's the purpose of using the same impulse response. And in this impulse response, you can see the indices n is equal to 0 lie at 1, and for n is equal to 1 the response is 0.9. So from this impulse response we can actually, this impulse response is actually denoting the system coefficients, and with the help of these coefficients we can write the system equation. And how we can write the system equation? We know that please remember that this is only true for FIR filters, for which recursive part is equal to 0. So we can write actually the difference equation with the help of this impulse response. We know that at n is equal to 0, which is no delay in the input, so x of n, and the coefficient of x of n is 1, plus the second coefficient, and it is delayed by one version, which is x of n minus 1. Here you can see n is equal to 1, positive 1, positive 2, positive 3, and in the difference equation, in writing the difference equation, we actually provide the delay equal to the amount of shift. This positive is transformed to the negative, and the same coefficient is attached to this same delay. For n is equal to 0, which is n is equal to 0, this x of n, the coefficient is 1. For n minus 1, we have the coefficient 0.9. So in this way we can form the difference equation with the help of impulse response, because impulse response is actually telling us the system coefficients, but this is only true for FIR filters. In the example 2, you can see we have three coefficients or three system coefficients, and indices lie at the first coefficient. So we can actually write the standard or difference equation for this impulse response. Y of n is equal to 1, one coefficient is attached with the 0 delay, 0 coefficient is attached with the 1 delay, and for second delay 0.8 coefficient is attached, or we can ignore this second term because it tends to 0. So x of n plus 0.8 x of n minus 2 is the response or the difference equation for this particular impulse response. Similarly, in example 3, you can say we have the impulse response, but interestingly we have indices lie at the last value. So it means the previous values lie at n is equal to minus 1, minus 2 and minus 3. But when we write the difference equation, we take reverse of it, which means at n is equal to 0, the coefficient is attached as 1. For the indices n is equal to minus 1, we actually represent it as n plus 1, and the coefficient is attached as 0. For n plus 2, the coefficient is 2, and for n plus 3, the coefficient is 0.7. The transformation from negative to positive is understood by another concept, that this impulse response is actually we are getting from any specific system, and we have indices of n is equal to 0 at the last value, which means that we are getting some response before n is equal to 0, which means this signal is actually advanced. So you can see the equation is representing the advanced version of signal or advanced version of input, which is already applied before the time instant n is equal to 0, because this expression is yielding the output at n is equal to 0, but it depending upon the advanced version of the signal, which means the values of signals are already taken and it is producing some output. So that's why we are obtaining output at n is equal to -1, -2 and -3.